Welcome back to Organic Chemistry. Today we're going to look at the different groups in this reaction, an SN1 or SN2 reaction, depending on what these groups are. What we're interested in is this attacking group, which we call a nucleophile, because it is attacking the positive charge on this carbon, partial positive charge on this carbon to be more correct. So this nucleophile attacks this nucleus, which is an electrophile. This nucleophile attacks this nucleus to give the leaving group chloride. The reaction could also go back in the other direction, in which case the chloride over there would be the nucleophile and the hydroxide here would be the leaving group. So what makes one of these nucleophiles better, stronger, more effective than another one? Looking at the halogens, we know that fluorine is a more electronegative atom than chlorine or bromine, and so the electron density is going to be higher if it's connected to anything else. But if it's on its own, it's fair. They've all got the same amount of electron density. They've all got one extra electron, so that removes that effect. Obviously, if they're connected to something else, the fluorine is going to have a higher effective share of electrons than chlorine will do. So purely from electronegativity, the fluoride ion would be expected to hang on to its charge, to not want to give it up, and so it would be not such a good nucleophile as the bromide ion, which is not so electronegative, and so therefore it's going to be more likely to give away its negative charge. However, there's a competing effect, and that is size. So why does size matter? Well, if the negative charge is spread out over a larger area, it's more stable, it has a lower energy. As if the negative charge is concentrated in a small area, it's less stable, which gives it a higher energy. So from the size point of view, the bromide or even the iodide ion is more stable, is less good at giving away its electrons, at being a nucleophile, than the fluorine. Why does size matter so much? We can think about it via the acids. So whether the base performs as a nucleophile is linked to whether it performs as a base, as an acid in its hydrogen connected form. So if we consider HBr, HCl and HF in this example, we know from basic chemistry that HCl behaves as a very strong acid. So in water it's mostly as Cl- and H+, but we also know that HCl is the sort of poster child of an intermediate bond. It also forms molecules, HCl molecules, that can be a gas. If we take anything else that forms chloride, so sodium chloride for example, it doesn't form a gas, it doesn't form molecules of sodium chloride, it forms an ionic crystal where the ions are still present even in the solid form. If we take hydrochloric acid, we can evaporate the hydrogen chloride as a gas, and so we can see that it forms molecules, that the bond between the hydrogen and the chloride is intermediate between ionic and covalent. So looking both ways, if we go to hydrobromous acid, this one, we discover that it's more acidic, that it is harder to make hydrogen bromide from hydrobromic acid. It's harder to extract it than it is the hydrogen chloride, and that it doesn't form molecules in solution even at very high concentration. Going in the other direction, HF, this is a known health hazard that you will have heard of. So how does the hydrofluoric acid do that? It does it as a molecule. The HF molecule is very strongly bound and is much more likely to behave like a molecule than the hydrogen chloride is. And the molecule HF passes through our skin as an uncharged particle that allows it to get through the fatty acids that make up our cell walls and get into our body much easier than HCl can, which is not very present as a molecule where it could get through. It's much more likely to be an ion, and ions can't get through an oil barrier, whereas HF can. What happens to the HF once it's inside our body is a different story, but what it tends to do is bind calcium. It forms calcium fluoride, and that is bad for us because it takes away calcium, which is a really important element in biology. So as usual, we have two competing effects. We have the electronegativity, which if we can make the atom or molecule charged or have electron density, it's better if it's not too electronegative, because then it's more likely to give away its negative charge. And we have the size, where the larger the ion is, the more stable it is in its normal state. So if we take a bromide ion, the negative charge being distributed all over the bromide, it makes it lower in energy than the fluoride ion. However, we're not in a vacuum, we're in some kind of solvent, so depending on the solvent, we can interact with this. If we take something that, like water, that interacts very strongly with smaller ions, we can make these more likely to exist. We can reduce their energy, we can make them more stable, which will make them less good at attacking things. If we take something that is non-polar, it will make all of them way more reactive because they are unhappy effectively. It's a bad thing to say, but they're effectively unhappy in the medium that they're in. The total charge is also important. So if we take a water molecule, it's a nucleophile. It can donate electrons from one of these lone pairs to something. For example, a hydrogen ion to form H3O+, but it's not as good at doing that as an OH-, which has an actual charge. So having an actual charge makes it way better. But let's consider the other direction, because we are considering leaving groups and electrophiles because they are the flip side of the same coin. If we take an alcohol with an OH group on it, we have to kick off OH-, which is not a very good leaving group because it's got a very high charge density over here. The oxygen is quite negatively charged. It's quite difficult to get that to leave. Whereas water is an excellent leaving group because it has very strong bonds to other water. So particularly if this water is leaving into water, this is an excellent leaving group. We can make it leave our organic molecule really easily if we can make it in the first place. So let us have an example of that. Got to do some drawing. So if we take an alcohol like this isopropanol, we can see that the oxygen here of the alcohol has a slight negative charge, and it has a lone pair up here, has another one down here. If we interact it with an acid of some kind, we can protonate it, and we're converting effectively our leaving group that could be OH- on this side to an alternative leaving group, which is H2O. So if we take a nucleophile that's negatively charged and push it in from the back here in an SN2 reaction, which we haven't thought of yet, so we've got maybe a chloride or iodide or a fluoride coming in, that would have to make this leave as an OH-. But if we protonate it first, it can leave as water. So looking here on Master Organic Chemistry, a website that I recommend you go and have a look at, we can see a primer on organic reactions, types of nucleophiles, which show us, first of all, we can go back to see nucleophilicity versus basicity, what makes a good nucleophile. First of all, we'll have a look in here so we can see lone pairs going over that. In this case, we've got OH-, we've got an amide, and we've got an alcohol that can all attack with a lone pair. Then if we make it more basic, so we make a better base out of it by having for example, ammonia group, then it will be a better, then it will be, this page also has a list of 3 characteristics of nucleophiles. So if we look at these 1, 2 and 3 here, if we increase the charge to more negative, it becomes a stronger nucleophile. So they've put it as the charge decreases, so it becomes more negative or it becomes less positive. The nucleophilicity increases as you increase basicity, which I would say is actually 2 and 3, because if we compare the halides, the iodide is more basic than the bromide, which is more basic than the chloride. Let's have a look at the next page as well. So I suggest you have a look at all of these pages. Let's have a look at the next page. What makes a good nucleophile? So this page really summarizes the page before, but it is telling us one important thing, that the nucleophilicity is measured by the reaction rate, which is important because the basicity is a thermodynamic property. It's measured by the energy, the reaction energy, because acid-base reactions are super fast, so the reaction rate is unimportant. They're all very, very fast, so the strength of a base is determined by the reaction energy, whereas in an organic reaction it's usually much slower, and therefore the kinetics becomes way more important very often than the energy that's given out, although there are of course exceptions. So in this case, very often a fast but not as strong reaction can trump a slow but very energetic reaction. The other 2, points 2 and 3, are recapping the other page. However, let's have a look at the 4 and 5. So if we change the type of solvent, and it says polar protic versus polar aprotic can dramatically affect nucleophilicity trends, and steric hindrance, which it calls bulkiness, can also affect nucleophilicity. So let's have a look at those. That's a link, hurrah. So if we take a solvent, now let's talk about those on the board. So that website then jumps straight into types of solvents and just mentions them by name, and we haven't spoken about that, so we ought to do that first. If we take solvents, we can see that there are different types. The simplest type of solvent would be something like hexane, which has very little interaction with anything. It's non-polar, so we call it non-polar, unsurprisingly. But if we take a solvent that is polar, it can be protic or aprotic, which is what they say. So if we take a polar aprotic solvent, it has no protons to give away, so it would be something like acetone. Acetone is a good example of a polar aprotic solvent. It's got a double bond to oxygen, so the oxygen is slightly negatively charged, this carbon is slightly positively charged, so there's a dipole, but it doesn't have a hydrogen on it that it can give away. If we take isopropanol, which has just got a hydrogen on here, this hydrogen has the potential to be given away to something else as a proton. It's not very protic because it's not very acidic. This isopropanol, this hydrogen bond, is not very acidic. So if we go up one further to acetic acid, we can see this hydrogen is very acidic. It's easily removed. Okay, its pKa is 3 or something. It's easily removed, so this is a protic solvent. This is also protic, but not as strong. Acetone is aprotic. It doesn't have a proton that it can give away, and that has a strong effect, as they say on their website. It has a huge effect on the nucleophiles, because the nucleophiles are very often competing between being a base and being a nucleophile. So if we take something that is a very good base and we put it into acetic acid, it will grab protons from the acetic acid and it won't react with whatever else we have in there. If we put it into isopropanol, it will struggle. If it's a very good base, it will steal this hydrogen and make a new nucleophile, which would be the isopropyl anion. If it's not a very good base, it won't do that. If we put it into acetone, it is a lot harder because the protons on here, the hydrogens on here, are not very acidic, so it's a lot harder to remove them. It is possible to remove them if we work really hard, but it's a lot harder to remove the protons on acetone than it is to remove this one on isopropanol, and it's extremely much more easy to remove this hydrogen from acetic acid. So if we have a competing reaction, it can switch the order around, because obviously the most effective nucleophile is also going to be a strong base, and if there are hydrogens in there, then that will interfere with the process and it will react with this instead, which might mean the second most active nucleophile is better. The example that they give on the web page, which I won't go back to, is that fluorine, chlorine and bromine and iodine, the ions of those are different in order whether they're in a protic solvent or in an aprotic solvent. So if we put them in an aprotic solvent, fluoride ion is a better nucleophile, but if there are protons around, the fluoride ion is distracted and the bromide ion or the iodide ions are better nucleophiles. It switches the order of the nucleophiles around because they interact with the protons in the solvent. The other thing they talk about, also not going back to their page, is steric hindrance. So if this nucleophile is very big, it will struggle to get in here. This is the isopropyl group, and it has the attacking point for an SN2 reaction will be the anti-bonding orbital of this carbon-chlorine bond. And to get to this anti-bonding orbital, the nucleophile has to come in from a specific angle, from behind, and it has to get between whatever is on the side here. The bigger this is and the bigger this is, the harder it is for that reaction to happen. So smaller nucleophiles can react better even if they don't have such a high reaction energy. Going back again to the point that the kinetics, the speed of the reaction, is important here. It's not just the thermodynamics. So if we make this bulky and difficult, even if the reaction, if it finally happens, gives out a lot of energy, a smaller nucleophile can be faster, and we will see typically the product from the smaller nucleophile that can get in better, or the longer, thinner one that gets in and attacks on here. If we take a simple SN1 reaction, so we take tertiary butyl chloride. In the first step it forms a carbocation, so the chloride group falls off. I haven't drawn it, I should have really have done. The stability of that depends very strongly on the solvent, because if we take a polar solvent, it can interact with this positively charged carbocation and reduce its energy. So this is the intermediate. It really exists, it stops there, and then it goes further on. So the energy of this compared to the energy of this is what determines the speed of the reaction. The rest of the reaction just follows on. We had the SN1 product where a nucleophile comes along, and it's going to come along from either the top or the bottom, because this is flat and it's got orbitals or an orbital that sticks out of the top here towards you and down away from you. It can attack from either side. There is an alternative reaction which I'll draw up now. So the alternative reaction, the elimination reaction, this proton, the H, on one of the methyl groups is removed. The electrons from the bond between the carbon and the hydrogen go in here and are absorbed into this orbital, giving up the neutralizing the charge. So this comes off as H plus somehow, and we form a double bond. We have to first of all work out what's going on here. We need something to take it away. So typically some kind of base will come along and remove this proton, or assist in removing this proton, and allow this elimination to proceed. The problem is that bases and nucleophiles are very often the same thing. So depending on what our nucleophile is, if it is also a base, it can also do this. The other problem is, if our solvent is a protic solvent, it can also cause this to happen. It can shuttle protons around, so it can help and interact with this reaction. Therefore, It's important because depending on what nucleophile we have, we can generate side reactions that suck really badly because we're making something that we don't want to make. It's reducing our yield, it's reducing the amount of product that we make, but even worse, it's contaminating the product and then we have to remove it, so it's another step, it costs time, it's very difficult. When we finally get into lab, you'll see that one of the most time-consuming steps is purifying your sample. So what we then have is a side reaction that does something. This is good and bad, because if we have a handle on this, if we can control this, we can decide whether we make a double bond or whether we make a substitution product. There is also an elimination reaction for the SN2 reaction, but because that's not our major part for today, I'm more interested in the strength of this as a base and the strength of it as a nucleophile, why that matters, and the solvent, because they influence the reaction very strongly. They influence the energy of this transition state, and they influence how easily this hydrogen can be removed.